So lecture 28 is on the algebra and geometry of volume elements, and in some sense this is really just a quick introduction to some the last part of this course as I've constructed it for you guys this semester. In particular, in the very last bit of the course, I'm going to talk to you about differential forms and how we can do calculus 3 using differential forms. This is a sort of short introduction to some of those ideas. Very short, really. But it also touches on some intuitive geometric understandings of the area and the volume element. So, basically here's the picture you can think about for the two-dimensional case, right? For the case of the area element for polar coordinates, you can think about this picture, and I essentially did this using finite differences in one of maybe the last lecture, right? But essentially this is the picture. I mean, you go from r to r plus dr, right? Like that. So that distance is dr. And then of course you go, from over here, d theta. That's the arc that you subtend infinitesimally. And so essentially the infinitesimal distance in the r direction is dr. The infinitesimal distance in the theta direction is r d theta. And so when you multiply those, you get dA is r dr d theta, So that's one way you could look at this thing. And of course here's this other argument, which is essentially the one I gave before, and the point is that the third order term we neglect, right? But there's another way of deriving this formula. So this is what I would say is intuitive geometric, all right? And what I'll introduce to you next here is what I would call algebraic. And it's the algebraic method here is the method of what's called the exterior algebra, or differential forms. And so there's this thing called the wedge product, and it's denoted by a by a wedge right here. And it's an associative product with the usual algebraic rules, except that it's not commutative in general. So for differentials, you have like df wedge dg is minus dg wedge df, and here I do mean the differential we talked about before, right? Remember we defined for a two-dimensional function like df was fx dx plus fy dy, so same differential we talked about before. But now I'm suggesting that you can take two differentials, put them together, and form something called a two-form. And formally speaking, they satisfy this rule. df wedge dg is minus dg wedge df. That means it kind of behaves like the cross product. For example, dx wedge dx is equal to minus dx wedge dx, which means that dx wedge dx is equal to 0. Likewise, dy wedge dy is 0. dr wedge dr is 0. d theta wedge d theta is 0. All right, so with all these basic ideas in mind, we can calculate dA. And I put a vector over it here because actually we should distinguish this a from the scalar dA, which was, I'm making a distinction here. dA, which some people would just say, well, that's just part of the notation for double integral, and then fine, I don't dispute that. You could look at it that way. But you could also look at it as the scalar infinitesimal area element in a heuristic sense. And I would like to distinguish this heuristic from this one. All right, and well, this actually isn't heuristic. It's a specific and concrete object, which we can define carefully. But anyway, so here we go. dA, let's say vector, dx wedge dy, but x is r cosine theta, y is r sine theta, and we take the wedge product, we take the differential, we get cosine theta dr minus r sine theta d theta, and likewise sine theta dr plus r cosine theta d theta. We take the wedge product of those, and basically the wedge product algebra satisfies the usual distributive laws, and you can bring scalar functions out like sine theta, cosine theta, or rather cosine theta, sine theta, dr, wedge dr. I just flip the order of sine and cosine, don't make anything of it. And like cosine theta times r cosine theta gives me this r cosine squared theta term, dr wedge d theta. And on the other hand, I get minus r sine squared theta d theta wedge dr. And then, of course, I get this minus r times r sine theta cosine theta d theta wedge d theta. But, of course, d theta wedge d theta and dr wedge dr are 0, right? As I was telling you, this is 0. This is 0. And this is minus dr wedge d theta. So what that means is that we can combine them, sine squared plus cosine squared, and just get r dr wedge d theta. That's dA vector. Now, so the reason I put a vector over here to distinguish it from the other one is, you know, I wouldn't think anything of saying dA is dx dy or it's dy dx, right? In some sense, that's just a prescription of how we set up the double integral, right? Maybe I'm indicating that was type 1 versus type 2 or vice versa, right? In contrast, dA is equal to this, but that's equal to minus r d theta wedge dr, all right? And so in other words, r d theta dr wedge dr and r dr wedge d theta, they're not the same dA vector. In fact, one is opposite the other in direction, and that minus sign basically encodes the orientation, all right? And so basically you could think of dx wedge dy as orienting the xy plane upwards, and dy wedge dx as orienting the xy plane downwards. And so that's the thing. And we'll see later as we talk about surface integrals that the wedge product of x and y is more naturally associated with the vector area element than, say, dx dy. Dx dy has no sense of up or down, whereas dx wedge dy has a sense of orientation. So there's a more natural identification of the wedge product of dx and dy with the surface area element. And again, I'm foreshadowing comments later in the course, guys. So don't get too worried about this section right now. It's really, I'm setting a stage for a larger discussion later. Okay. And I should mention to you that wedge products and determinants are closely related. So, just to expand on the algebra of the wedge product, essentially it's the algebra of determinants. And here's the critical, critical idea, which is if you take the columns of A, column 1, column 2, column n, that's what AX1 hat, AX2 hat, AXN hat is. Like column J of A, that's A times EJ in linear algebra. But here my notation for EJ is x hat sub j, right? So that is nothing more than the jth column vector. So if we take the wedge product of the columns 1, column 2, column n, we get the determinant of A times the wedge product of the basis vectors. And so that identity allows you to calculate determinants implicitly from wedge products. In fact, some linear algebra texts take that as the definition of determinant. So here's just a quick calculation on how that goes for the 2x2 case, and maybe you'll find it instructive, I don't know. So if I have A, B, C, D, then column 1 is AC, and column 2 is BD, right? So I've written them in terms of hats, but this would be AC, right? And this would be BD, just to echo my previous comment. And so when you take the wedge product of those two columns, like down here, what happens is you get these four possible terms, right? And again, as I said, the wedge product of something with itself, when it's a vector, a wedge product of a vector in itself is 0. Whereas these wedge products of vectors, distinct vectors, gives you what's called a 2 vector, for what it's worth. But and so admittedly there's also, we could talk about multi-vectors, or we could talk about differential forms. We could talk about, let me stop peppering you with more terminology and stick to the formal presentation here. Anyway, the point is, this gives me AD minus CB because we flip the order of these, we get a minus. But that, of course, is exactly the determinant of the 2 by 2 matrix ABCD. And so we see that the determinant of A is AD minus CB, which is our usual formula for the 2 by 2 determinant, right? And I'm just introducing to you some of the basic algebraic features of the wedge product. I have much more to say about it later. We'll see that the wedge product can be used to encode dot products and cross products all at once. It's really quite neat. But anyway, just a word more back on, so I said algebra and geometry, so here's more on the geometry. So the geometry of spherical and cylindrical volume elements is essentially given here. So you can think about like a little sector, almost like a piece of cheese, isn't it? So this is the cylindrical infinitesimal volume element, and so so the dA on the top, that's just the RD theta. All right, no wedge here. We're just thinking about the scalar area element, and the height is just dz, right? So if I take dv, I take dz times dA, that gives me dv. That's like the just straightforward intuition here. And of course, that is what we have previously said the cylindrical volume element is. It's RD theta dz, right? Now in this case, we have dl, r is dr. We have the infinitesimal length in the theta direction is RD theta. We have the infinitesimal length in the z direction is dz. So as a general point of order in this way of thinking, your volume element is the product of the infinitesimal area lengths in each of your coordinate directions. And this works as long as the coordinate directions are what are called orthogonal. And so that's exactly what we have up here. Now over here it gets a little bit, I'll zoom in here a bit because it's kind of busy. Right, the spherical volume element, it's I don't know, I never try to draw this in class, it never goes well. So I have to swing out in an infinitesimal amount in the theta, in the rho, and also in the phi direction, right? So like swinging in the rho direction, just like spherically expanding outward. And of course the the infinitesimal change in rho, we can just say is d rho. But in contrast, if you think about swinging theta, you have to think about the radius that theta is swinging along is actually r, right? So dl theta is r d theta, but in spherical terms that's rho sine phi d theta, all right? And then dl phi is swinging off the z-axis, so there you're actually rotating by the full radius rho, so you get rho d phi for that one. And when you multiply dl rho by dl theta by dl phi, you get exactly two. You get two rows. You get your sine phi. You got your d phi, d rho, d phi, d theta. And so some people find great comfort in deriving the spherical volume element using this geometry. And I say deriving somewhat loosely, but this is a more geometric way you could understand why that sine phi is there. All right, it's because when we rotate in the theta direction, the radius we're rotating by is the cylindrical radius, which in terms of sphericals is rho sine phi. So, yep. And but then of course the chief, getting back to the algebra again, the beauty of the differential form in the algebraic method is that it's not specialized to 2 or 3 dimensions. These wedge products I'm telling you about, we can equally well do for n dimensions, and as such it gives us a way of describing oriented n-dimensional spaces, which is what you need to extend the treatment of integration past surfaces or curves or volumes. And in fact, differential forms are the natural object to study the calculus on curved spaces of arbitrary dimension, which of course is important to more than just mathematics. I mean, fluid mechanics and in fact, all of modern physics is, like string theory, for example, is largely written, at least partly, in terms of differential forms, because vector fields that we'll soon study are really only, well, they're most useful in 3 dimensions, let's say that way. Now finally, this calculation right here, well, this one is not especially surprising, but I mean, it's pretty neat. But this one down here, this calculation, when I saw this for the first time, it just, I have been in love with differential forms ever since I saw this, because to me it was just, to me when I first saw the Jacobian that I've shared with you guys in the previous lecture, it just seemed to be mystical to me. Like, why was there Jacobian? Where's this Jacobian coming from? Yet this differential forms method, it's just, you know, hand-to-hand combat. Just the differential you already learned and this little wedge product, you know, and somehow that asymmetry, that skew, the skewness, the dx wedge dy is equal to minus dy wedge dx, that property, you know, paired with the differential, somehow allows you to calculate bit by bit, line by line, the, you know, rho squared sine phi d rho d phi d rho wedge d phi reg d theta. And so essentially this is just a different, now that I'm a little bit older and wiser perhaps, I understand that this is just a, you know, a different notation for calculating determinants, really. But for whatever reason, this particular calculation just convinced me that differential forms are really neat and something worth studying. So I persist in that opinion to this day. Now at the end of the chapter, of course, as always, I have oodles and oodles of solved problems. I would remind you that they're there, and many of them have solutions, and many of those solutions are at least mostly correct. So do keep those in mind as you're studying. If the absurd number of examples I've given this chapter aren't enough, you also have these to look at. There are no examples, I don't think, on differential forms in this, and I don't think I've really asked you any homework on those yet. If I have, you can skip them. We'll cover differential forms towards the end of the course. So anyway, thanks guys. Up next, what's up next? What is up next? Lecture 29, which is on vector fields and the gradient operator. That's after test 3. So our next order of business is test 3, which covers optimization, and of course the integration of 2 and double and triple integrals, Cartesian variable bounds, change of coordinates, the whole thing, right? But test 3 will focus mostly on lectures 21, 22, 23, 24, 25, and 26, and 27, but not so much 28. 28 is really just intuition. So thanks, guys.